So if not, let's move on to the last example. Okay. So in this last example, we're going to utilize this property here from the table. Okay. So this is sort of a dual property of the multiplication property, right? So previously we showed that if you have multiplication in the time domain signal, then the Fourier series coefficient would be equal to a periodic convolution. Okay. Now this is true the other way around. If you have a signal Wn that is equal to a convolution between two signals x and y, then the Fourier series coefficient will be equal to the product of their respective Fourier series coefficient multiplied by the period capital N. Okay, so utilizing this property, we're asked to answer the following question, right? So suppose that Wn is periodic with fundamental period capital N equal to 7, and that the Fourier series coefficient takes on this form here. Okay. Now, by observation, you can view this CK as 1/7 times this sine over sine squared. Okay. So by observation, we can view CK as actually, let's say 7 times dk squared, okay, where dk is 1/7 sine 3 pi k over 7 sine pi k over 7. Okay. Now, why do we want to write it like this? Okay. So I hope that a Fourier series coefficient like this looks familiar to you, right? Because we just used it in a few previous examples. Okay. So in particular, this is actually the Fourier series coefficient of a periodic square wave, okay, with n1 equal to 1 and period capital N equal to 7. Okay. So this actually is the Fourier series coefficient of a signal, okay, of a periodic signal okay, that is a periodic square wave with n1 equal to 1 and period equal to 7. Okay, so you have a 1 here, here, and here, right? From -1 to 1, 0 here, and repeats itself again here, 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 and so on. Okay. So if you are able to observe this fact, right, if you are able to observe that CK is equal to 7 times dk squared, where dk is actually the Fourier series coefficient of this periodic square wave, then by the property above, you know that the signal Wn that you're looking for can be obtained by taking the periodic convolution of x of the signal x and itself. Okay. So hence, this Wn that you're looking for should be equal to the convolution between x and itself for R summing over one period. Okay. Now, in particular, we can limit this summation from -3 to 3. Right, we're taking this summation over 7 consecutive indices, okay, of xr, x of n minus r. Okay. Now, instead of doing this directly, right, since we're only limiting our summation over only one period of the signal xr, okay, this is equivalent to looking at the summation over some effective signal xr hat, where xr hat is equal to xr for r within this range, but 0 everywhere else. Okay, so where this x hat n is equal to xn for n between -3 and 3 and 0 otherwise. Okay, so if we replace xr with this x hat of r, we can then take this summation from -infinity to infinity xn minus r. Okay. So, right, so here we have this example where xr looks something like this, right? So here n1 is equal to 1, so you have ones from -1 to 1, right? 0 for 2, 3, 4, 5, and then 1, 1, 1 again, right? So this thing repeats itself, you know, every capital N equal to 7, right? So 1, 2, 3, 4, 5, 6, 7. Okay. Now I want to take the convolution between xr, which is this, and itself. Right. So x of n minus r is xr flipped around and shifted to time n. Okay. So x of n minus r is xr flipped about the origin, but then moving the midpoint to n. Okay. Now, instead of looking at xr directly, we look at the effective signal x hat of r, right? That is equal to 0 outside of the range of summation. Okay. So the reason for doing that is because, you know, then we have x hat of r that looks cleaner, right? We don't have to worry about what happens in other areas of the time index. Okay, and then we take x hat r, convolve it with x of n minus r, right? That is flipped around and shifting the center to time n. Okay, and multiplying these two signals pointwise and summing it up gives you the signal Wn that you want. Okay. So in particular, So suppose you want to compute W0, right? So W0 is summation, X hat R, X of N minus R, R from minus infinity to infinity. Okay, so here N is 0, right? So this is 0 minus R. Okay, so this X of minus R is simply X of R flipped around, right? So when you have X of R flipped around and multiplied with this, you have 1, 1, 1 here and 0 everywhere else. Okay, so this is just summation R from minus 1 to 1 of 1, which is 3. Okay. So similarly, when you compute X of minus 1, W of minus 1 or W of 1, right? You take the convolution, you multiply this X hat of R with X of N minus R, where N is equal to 1 or minus 1 in this case. So if you move the center point to 1, then you will have 2 points that overlap. So when you multiply, you get 1, 1 at times 0 and 1, and 0 everywhere else. So when you sum that up, W1 is equal to 2. Okay. So continuing this fashion, you can find W of minus 2 and 2, which is equal to 1, and then W of minus 3, W3, that is equal to 0. Okay, so therefore you have specified what the signal looks like over one period. Okay, and this is the plot of your final outcome. Okay, so do we have any questions here?
老师可以再讲一次为什么那个-1等于1，然后-2等于2吗
？OK， 这个其实就是，就是说这个我没有去讲 detail， 因为它其实就是算一个 convolution 而已。那这个我想大家回去都可以自己算 ，OK？ 那其实，你想想看，你要算 convolution， 你就是，你这是 x hat of r，right？ 然后你这是 x of r， 你要把它 flip around， 然后 shift 到比如说如果 n 等于1的话，就是往右边 shift 一格。那往右边 shift 一格，就是说你 point y 相乘的话，这个1就会跟这个1相乘，这个1跟这个1相乘，那其他的地方相乘都是0。所以说你把它加起来的话，就会等于2。OK， 那这个 detail 我相信大家回去应该是有办法自己算，所以我就不把它那个写出来这样子，好不好？我们这个回去试试看。
好，谢谢。
好，谢谢。
那个教授。那我想要问一下，那个就是上一页有那个提出来的1/7，那新的系数要乘回去那个1/7吗？不对，7倍啊，7倍 ，ck 等于7的 dk 平方这里。
因为我在 dk 里面有一个1/7，所以 dk 平方就有2个1/7嘛，那跟乘7以后就剩下一个1/7的。
所以后面 wn 算出来后要是乘以7嘛，就是。
哦，对，要，对，你说对了，应该要。哎，没有，不用，对不起，对，因为这个，就是说，因为我现在这个7就是这个 capital N， 对，所以我如果直接对照这个跟这个的话，那么它的 time domain 就是原本的这个 x 跟他自己的这个 convolution。
好，应该大概懂。
OK， 所以其实就是套用这个公式啊，对。那这个公式 其实就是就是鼓励大家自己回去推导一遍。事实上前面的那些那整个 table 里面的公式，我都鼓励大家自己推导一遍，我觉得这个会比较有印象。OK， 虽然说这个推导应该都是蛮 straightforward， 大家可能觉得就是很反复，但是就是说推导一次就会比较知道它是怎么来的这样。OK， 还有没有其他的问题？Okay. All right. So if not, let's move on. Right. So up to this point, we have talked about whether or not you can represent periodic signals either in continuous or discrete time in terms of its Fourier series representation. So Fourier series representation is basically a linear combination of harmonically related complex exponentials. Now, the reason for looking at this is because, if you can write signals as, a linear combination of complex exponentials, then it's, the input-output relation of a linear time invariant system becomes, you get a, easy and intuitive way of looking at the input-output relation of a linear time invariant system. Okay. So in particular, we showed previously that, this, so the reason for this is because this complex exponential is a eigenfunction of linear time invariant systems. This means that if you input a complex exponential to a linear time invariant system, the output will also be the same complex exponential, except for this gain, which can be evaluated by this formula here. Okay? So if you input this complex exponential, you get the same complex exponential, but with a different gain. And this gain depends, can be evaluated from the impulse response. So this is true also in the discrete case, where if you input, x of n equal to z to the power n, then you get the same z to the power n at output scaled by this gain h of z, which you can also compute by the impulse response. Okay, so this holds in general for any s and any z. So in general, if you're looking at general complex values of s and z, then we call this h of s and h of z system functions. Okay. But if you're looking at particular cases where s is equal to j omega or z equal to e to the j omega, then these complex exponentials correspond to pure frequency components, and therefore the system functions, right, this hs and hz are then called frequency responses. Okay, and we're going to be looking at these cases most often, right? Okay. So consequently, in continuous time, if you say that your signal x of t can be represented in terms of this linear combination of these complex exponentials with pure frequency components, right? Then the output y of t would be a linear combination of the same harmonically related complex exponentials with the gain altered by this h of j k omega naught, where k omega naught is the corresponding frequency of this complex exponential. Okay? And this value you can readily compute using this formula up here. Right. So you can see here that, by passing a signal through a linear time invariant system, the signal is modified. This linear time invariant system modifies each frequency component individually, right? Using this gain here. Okay. So an LTI system modifies the gain of each frequency component individually. Okay. So this helps you gain further insight about what happens when a signal goes through a linear time invariant system. Right? You can sort of see, which frequency components this system amplifies and which frequency component this system maybe suppresses. Okay. So let's look at this example here, which is the same as example 3.2. Okay. So here we have x of t, right, equal to this summation from -3 to 3 ak e to the jk 2 pi t, okay, with coefficients given down here. So suppose that this signal is passed through a linear time invariant system with impulse response equal to this, okay. Now suppose you want to know, right, you want to obtain the output signal. Okay, you want to obtain the output signal. Right. So what we can do is that we can first compute the frequency response to this system. Okay. So for this system, we can compute the frequency response h of j omega as the integral of h of tau e to the minus j omega tau d tau. So if I plug this inside, I then have an integral from 0 to infinity e to the minus tau e to the minus j omega tau d tau. Okay, so if you work this out, you get 1 over minus 1 plus j omega, right? Because you get minus 1 plus j omega tau in the exponent here, e to the minus 1 plus j omega tau for tau with the upper and lower limits 0 and infinity. So if you plug this in, then you get 1 over 1 plus j omega. Okay. So we know that if the input is this linear combination of complex exponentials, then the output y of t must be a linear combination of the same complex exponentials okay, times the gain h of j two pi k. Okay, so if you take this, plug it inside, then what you get is summation k from -3 to 3 ak 1 plus j omega e to the j, oh, I'm sorry, 1 plus j 2 pi k e to the j k 2 pi t. Okay. So let's denote this. So this is the coefficient, the Fourier series coefficient for the output signal y of t. Okay, so let's denote this as bk. Okay, so if you plug in, ak given above, right, you will find that b0, okay, b0, which is a0 over, okay, over 1 plus 0, okay, is 1, right? b1 is equal to 1 over 4 times 1 over 1 plus j 2 pi. Okay. b minus 1 is 1 over 4, 1 over 1 minus j 2 pi. Okay. And so on and so forth. Right. So b2 is 1/2. 1/2 is a2, right? Times 1 over 1 plus j 4 pi. b minus 2 is 1/2, 1 over 1 minus j 4 pi. b3 is 1 over 3, 1 over 1 plus j 6 pi. And b minus 3 is 1 over 3, 1 over 1 minus j 6 pi. Okay, so these Fourier series coefficients for y of t are obtained by simply plugging, different values of k into this formula here with ak given in the problem. Okay. Now, if you look at this, you will see that b1 is a complex conjugate of b minus 1. b2 is complex conjugate of b minus 2, and same for b3 and b minus 3. Okay. So we know that if this is the case, right, so notice that bk is equal to b minus k complex conjugate for all k. Right. So this means that it is conjugate symmetric. Okay. And when this is the case, we know that the signal must be real. Okay. So suppose we write bk, right? So if bk is complex, right, there are two ways to represent it, right? We can either represent it in terms of its magnitude and phase, okay? Or we can represent it in terms of its real part and imaginary part. Okay. Now, since bk is equal to, b minus k complex conjugate, this yt here can be represented in a more compact form, equal to 1 plus 2 summation k from 1 to 3, the real part of dk e to the j 2 pi kt plus theta k. Okay. And this would be equal to 1 plus 2 times summation dk cosine 2 pi kt plus theta k. Okay. Or if we represent bk as, ek plus jfk, then we can write this as, 1 plus 2 times summation k from 1 to 3 ek cosine 2 pi kt minus fk sine 2 pi kt. Okay, so these are just alternative expressions for your output signal y when your input is real and therefore the output is real. Okay.